Good evening, 26th May, 2023. Well, we're reading Fourier analysis and boundary value problems and contributions to nonlinear PDEs and Emery lactosis proofs and refutations, partial differential equations basic theory. That's pretty good. It's a sort of graduate introduction to basic theory of PDEs, about 500 pages. And talks about at the end, it gets into vector bundles, and it's nice when you get to higher level theorems about comprehensive objects like vector bundles, because they can get into things. Here he talks about Sard's theorem. It's interesting that many theorems are named for people, and so you have to kind of learn the field and learn the history of things and learn who's who and about how they're associated compared to something like a vector bundle, which you might talk about Poincare, or here he talks about a Hausdorff topological space, and which properties go into these things, which makes for things like topological spaces and Hausdorff spaces, and Tychonoff's theorem, Borel spaces, Banach spaces. Banach spaces are a little bit closer to Hausdorff spaces, I imagine. Vector bundles, tangent bundles, the Riemannian metric tensor, which is so familiar as relevant to gravity. It basically represents for Einstein's theory, it's like space-time, it's flat. How is it curved? Well, anywhere there's a gravity well, like a planet, it's a Riemannian metric tensor, and everything falls into it. Okay, all right then. Which way is gravity? Well, it's down. So space-time is curved? Yeah, it's flat. All right, hey, thanks, Einstein. He's like, sure, it's great. Haar measure, there's different means of measure. Talks about the unimodular, and so there's it gets into Lie groups and Lie algebras, which is really a pretty high level approach eventually. There's a book here about it. Reading about differential geometry, curved surfaces and manifolds. This is this theory of unimolecular gas phase reactions. Thermally induced gas phase reactions. When I said unimolecular, that is not so relevant to it, but there's different gas laws. There's kind of the fundamental and the Boyle's, and there's different definitions of calories for first and second law of thermodynamics and these kinds of things. So he talks about the limiting case, in terms of oscillators, and the semi-classical Marcus and Rice approximation about the total energy of the 0-point vibrations in Rabinovich and Deason, a semi-empirical factor in the semi-classical model, which is about, here it's been about the degenerate and the deconstructive account. The deconstructive account is like sub the elements. What are these elements that make it so? How is it arrived at this quasi and pseudo make it so that from points they form a line? When via induction they do not. They always would just be more points, but they'd always have room between them. Or how from a line do they form points? Because just splitting it into intervals, they do not, until they're a degenerate interval. And yet that's still an interval, not a point, or ... How is it that in the middle it is making that fully divided, not dividing it, but having it divided, having a completion? This is called a fixed point of the space. What's infinity? Well, it's kind of a fixed point. And what does a fixed point mean? Well, it deserves its own definition, and I'm not really ready to provide it. But it sort of means that under various forms of transformations, it's the fixed point, the fixed star, the reference, and this kind of thing. So we might say, well, the origin is everywhere. Is origin a fixed point? Is often, it's often considered that. How about anything that's singular? And thus anything that everything else is homogeneous, and we can consider it as like a smooth passage which we're swimming through. We can swim, but this is a vortex or anything that's singular. It's like, well, then that's singular, and is it a fixed point? Yeah, in a sense it is. But I'll look some more about fixed point, because in certain spaces they'll define like a fixed point. What's a compactification of the naturals? Well, it's like adding a point and an infinity. Does it make the naturals compact? It's like, well, if you inspect the naturals and the definition is compactness, sometimes you'll be surprised that what are these infinite constructs would have vacuous or trivial properties that make it so that they kind of fulfill being one of these others, these kinds of things, and that they have multiple models because it's out in the infinite, and so out in the the great continuous or whatever. That's definitely non-technical. But the idea and point is being that there's standard and non-standard models of integers, and so many famous numeric conjectures about roots and powers and integers, like various conjectures of Goldbach, or even stuff like Raymond's conjecture, and these things, they actually have multiple models. And so one thing I was happy to find the other day and reading these books and all this kind of stuff, and there's, what is this about, like, here's this theory of unimolecular reactions, and there's this, what is this, macroscopic theories. Here's a couple of great books from Hermann about this differential vector bundles, the vector bundles and their differential analysis, and this that's kind of relativistics writ large, relativistic dynamics of the day. And you get into gravity and Yukawa potentials, and then this is differential topology, and you get into Yukawa potentials. You got Kaluza-Klein, which is like, well, we got 4 plus 1 or 3 plus 1. We got 3 plus 1 space plus time dimensions. Or if you don't need that at all, you can just use a time direction and have an array of time from the origin, say going backwards, and the whole thing just kind of pulls that forward. The great crawling spider of time in space-time. But in its own web, you know. And then the 5th dimension is called like Kaluza and Klein, add an extra 1. For what? Well, it's for pre-projection. Whatever you need that ends up being, that would not be bookkeepable, you can bookkeep in this higher dimension. That bookkeeping is this terms of basically keeping accounts of things so that you have enough extra data left over to make something. So the whole point of the 5-dimensional space-time of Kaluza-Klein is to just have an extra scratch pad dimension. And then you can give it to, in the mathematical interpretation, is just orthogonal to the other ones, depending on which geometry there is, or how about that's a space, or what tensor carries from space to space, these kinds of things. Then all these notions of higher dimensions are basically just higher dimensional bookkeeping that still has to fall back in the original. And that's even why it's like, well, still this space-time spider has to fall back and curl up into one little dot, or one little dimension called a hologram dimension. And well, how can that be that you could have this 3 dimensions of space in 1 dimension? Wouldn't that not be enough? Well, it's like, no, you can't really think about it linearly. You can't really like divvy up the coordinates and say your 1st dimension, your 2nd dimension, your 3rd dimension, or your height, depth, and width, or what. But you can kind of think of it, if you think of it like that the negative infinity is for one, and infinity is for another, and then make a great big circle, and then it just kind of falls in the center. You can kind of imagine that you could use that to paint a cube and have it that the changes in that according to this kind of geometry would just be like actions in the cube that are lines, you know, that these kind of arbitrary orbits and trajectories in such a space make it so that you can imagine that the 3 space dimensions kind of fit in 1 dimension of the numbers. Like it was like there's only 1 continuum ever invented by the universe that has everything in it. It's continuum. Well, it's a linear continuum? Yeah, if need be, and it's called a hologram. And then the space is just above that, and it just tents itself out quite naturally, and it tents itself in quite naturally. It's like, well, that's the simplest reason why there are 3 dimensions and space, and why it's a natural thing. It's just a natural feature of the numbers. Well, all right then, what about time then? Well, it's just kind of falling out of time, falling into time. And that's why it just kind of keeps on spinning around and around, that the universe naturally for us just, you can imagine at the very distant ends of it that's how it's spinning around. Then the idea is that then, well, if we're only going to have 1 force of gravity, how's that then? Well, it's just kind of like a fall gravity, and so the field of it is coming in from everything, and the earth beneath our feet basically just blocks the rest of the universe on that side. So because we're just falling together, we just kind of fall to the earth. So you can accelerate away from it, and it's pretty similar that once you get up and above it, then it's not just a point, but it's kind of this shadow, or it's well, or whatever. And so then that has the same solution as like Newton's inverse square notion proportional inverse square to distance, proportional to the product of the masses, and inverse proportional to the distance, inverse square proportional. It has the same solution, just as a matter of fact, and also it helps explain why it's inverse cube up close to black holes, and it's inverse very far away in galaxies and such, which appears to be. So these are the kinds of things that go into the things. So when talking about the vector bundles, then I found this book by Lefschetz. And so it here is written by S. Lefschetz, long life alkaline paper. His important book, Analysis Situs at Geometry Algebraic. And he talks about things like algebraic varieties, which are kind of like vector bundles in some senses. And when you get into different fields and they have this different names for the same things, is one thing, because then you can at least assign them, say this is mathematically the same as that. They model each other. They're the same. There's an extensionality, makes them the same. When they have the same names and mean different things, that's when it gets into the dynamics of the definition. And one reason why we kind of have a unified mathematics and use the same names for things, they don't like rename formulas and theorems too often, because they've always been that way. They don't really, they do come and go in and out of fashion. And for example, you know, after World War II or whatever, like there was a whole culture of results that were just kind of canned, you know, paint canned, ignored. That all still lives in Hilbert's infinite living museum of mathematics. But there are matters of cultural reception of the originators of the ideas and the concepts of the ideologies of the fields of mathematics. And I'm kind of partial here to Lefschetz. He describes about this time that he writes in this introduction that from 1911 to 1924, these circumstances was most invaluable in that it enabled me to develop my ideas in complete mathematical calm. Thus I made most use, most uncritically, of early topology a la Poincare, and even of my own later developments. Fortunately, someone at the Académie des Sciences, I always suspected Emile Picard, seems to have discerned the harpoon for the whale with pleasant enough consequences for me. And so I enjoy this because here's what he said. From the P-naught formula of Picard, applied to a hyperelliptic surface phi, topologically the product of four circles, I had come to believe that the second Betti number, r sub 2 phi, equals 5, whereas clearly r sub 2 phi equals 6. What was wrong? After considerable time, it dawned upon me that Picard only dealt with finite 2 cycles, the only useful cycles for calculating periods of certain double integrals. Missing link, the cycle at infinity. That is the plane section of the surface at infinity. This drew my attention to cycles carried by an algebraic curve, that is, to algebraic cycles, and the harpoon was in. So, for example, these days that would be like, well, that's terrible. I mean, harpoons are for gaffing whales and such. And we in this of interest in the society these days to save the whales. And it's like, still, it's a gaff, not a gaff kind of a thing. Lefschetz's general plan is to present the first concepts of algebraic geometry, then follow up with the early algebraic topology of Poincare, plus some of his own results on intersections of cycles. He will then discuss the topology of an algebraic surface. Next step will be a summary presentation of the analytical contributions of Picard, Savary, and Poincare, leading to his work, application of topology to complex algebraic geometry, including with rapid consideration of the effect on the theory of abelian varieties. Now, when I learned about Abel, for example, I was most familiar with what he had going on in group theory or something like that. And it's established that when you talk about the commutative property of a group, it's also called the abelian property. And so I was like, okay, great. But then you'll find a lot of times there's kind of two kinds of connotations. There's like Hausdorff is touched many different things, and so it almost represents this whole methodology. And someone like who's pretty particular is only related to one particular thing, like Nicomachus or something like that, you know. it's like the sum of the squares and the sum into the sum of the cubes. There's a closed form relating them or something, which is pretty great. And when I discovered that, I was like, oh, great! I discovered some of these sums of powers that add up to other things. That's pretty interesting. And they have derivations that kind of so follow. And number theory is a great field, and I don't know much about it yet. And then there's Euler or whatever, and it's like, well, what about Euler? It's like, well, if you're dealing with the infinite series this way, you can thank or blame Euler, or ditto Gauss or something like that, you know. And then there's somebody like Dirichlet, you know, and then Riemann is like, well, if you got Riemann, you kind of need Lebesgue and then Stieltjes, or if you got Riemann, then you kind of need Lobachevsky after Euclid or what, you know. And so these various kinds of schools of men are like so. So Abel then is also involved in this algebraic geometry, and was also discussed in terms of some of the developments of the Fourier analysis about Riemann. In its early phase, Abel, Riemann, Weierstrass, algebraic geometry was just a chapter in analytic function theory. The later developments in this direction will be fully described in the following chapters. A new current appeared, however, under the powerful influence of Max Noether, who really put geometry and more birational geometry into algebraic geometry. In the classical memoir of Brill and Noether in Mathematics Annals in 1874, the foundations of geometry on an algebraic curve were laid down, centered upon the study of linear curves, series cut out by linear systems of curves upon a fixed curve, fxy equals 0. Here I'm interested, for example, for the identity dimension, that fxy equals 0 is like x minus y or y minus x. The absolute value of x minus the absolute value of y, or vice versa. It's 0. X over y minus 1. Well, that's just... But anyways, it's sort of in the identity dimension, at the value is its own root. About all these roots of the identity dimension and this kind of thing in the things. A new current in the classical memoir of Brill and Noether, Foundations of Geometry on an Algebraic Curve upon a Fixed Curve. This produced birational invariants, for example, of the genus P, by essentially algebraic methods. Now, Lefschetz doesn't bother too much to establish all the preliminaries, but it's expected that his definitions kind of catch up and that he uses them systematically and thoroughly throughout. And what I really appreciate about his quote after he talks about Picard and Saveri and Enriquez and Castelnuovo Enriquez and the members of this Italian school, the Italian geometers, is that Lefschetz sets himself up as a geometer, not an algebraist. And so that his algebraic geometry is an algebraic geometry, not an algebraic geometry. He puts the emphasis on the geometry, not the algebra. The theory of the great Italian geometers, like Noether, is of algebraic nature. Curiously enough, this holds in good part regarding the work of Picard. This was natural since in this time, Poincare's creation of algebraic topology was in its infancy. Indeed, when it arrived in the scene in 1915, it was hardly further along. About 1923, I turned my attention to fixed points. Now there's some talk about fixed points, which took me away from algebraic geometry and into the more rarefied era of topology. I cannot therefore refer even remotely to more recent doings in algebraic geometry. I cannot refrain, however, from mention of the following noteworthy activities. 1. The very significant work of W.V.D. Hodge. I refer more particularly to his remarkable proof that an n form of V sub q, which is some algebraic variety in dimension q, which is of the first kind, cannot have all periods 0. That's something that I would look to approach as to confirm that how it's so, and what minimal model establishes is so. The idea of this deconstructive account is to be able to arrive at something like the Fourier analysis was talked about as just kind of a template. In fact, that's the whole idea of abstraction in mathematics, is to figure out what kind of template can make it so. Because then however you can replace and rebuild the template, you can arrive at the same kind of model for it. And so for however you want to apply mathematical modeling and dynamical modeling to anything, right? For example, physics. But then this other approach is the idea is that I already have these particular models that include like points at infinity, or that's non-standard. So the second thing I want to do, after understanding a little bit well enough, a walk through of the derivations so I can be pretty sure that I've seen the assumptions that go into the derivations, how to deconstruct those, and because I've fully deconstructed the elements fully to elements of a universal total theory of mathematics called the null axiom theory or something like that. And I built the geometry up out of that from this line drawing, the spiral space filling curve of this origin from that, and then arrived at something that's like Euclid's above that. How to otherwise then apply these sorts of non-standard but still correct in their models results, because I'm aware of that there are standard and extra standard and non-standard and super standard models of the infinite. How to go about this that cannot have all periods 0, but what if all periods are infinitesimals or something that are non-zero? And then 2, the second point, this really made me happy when I read this from Lefschetz. He talks about Bourbaki and the systematic algebraic attack on algebraic geometry by Oscar Zariski and his school, and beyond that of Andre Weil and Grothendieck. I do feel, however, that while we wrote algebraic geometry, they make it algebraic geometry with all that it implies. So there is a sort of disconnect between the geometers and the algebraists. It's like Vitali and Hausdorff have a derivation of the Banach-Tarski theorem or paradox. But Michelski and algebraists have one much later, because it was kind of rewritten in a sense for algebraic geometry and using the fundamental theorems of it instead of geometry. And so for a long time, algebraic geometry and algebraic geometry have had a disconnect. And there are many different things that are the things that hold up in the middle of it that are so extreme, like doubling spaces and Vitali's measure and revitalizing measure theory for Hausdorff geometers is a big thing. So when I saw Lefschetz write it this way and kind of calling out that there is a difference, because algebraists are like, we're also abstract that it's up here above this, so everything must be like this way. There's not a model where they don't have a model of things, but there is, and vice versa. But you gotta have both in a sense, and geometry wins. Geometry wins. So this made me happy. So then he goes on, and then he talks about differential forms and definitions of varieties in the function field and models of function fields and complex rational functions be identified, mod F, this field. And so, and about the singular and non-singular, and singular and not as non-homogeneous, and about the Cartesian and the algebraic varieties. It's one-sidedness when we say the commutative and non-commutative is abelian and non-abelian. Say abelian one forms of the Riemann surface. So this is an example of a distinct identification of a particular variety, whereas of course by now the word variety is overloaded, and we might often just read space. The n-dimensional variety of polynomials or hypersurfaces of projective space in which the variety had no singularities is like manifolds. We might talk about that in topology as words these days. It's about the manifold and the bundles after the sheaves. So first you kind of take sheaves, and then you get bundles. And he talks about the pencil, which is like a surface, about like a surface defined by a constant, kind of like the ordinate or the abscissa of a function compared to the axes that it falls to, or point or orthogonal to it. Then he talks about differential forms on a curve. Let the curve be fxy equals 0. Let m be its degree. All right. Like x quadruple prime minus y quadruple prime. Its one forms are said to be abelian. An adjoint to f is a polynomial phi sub n xy, n is its degree, vanishing at all double points. So he mentions double points, and that's a pretty interesting idea, because it's anywhere that it seems like that there's a splits or the singular terms. I'll need to learn more again. Any mistakes are my own. What I wanted to read from was some of the analysis Situs, and so we think back to Poincare and the analysis Situs. So the analysis Situs is this whole idea of development, and when it comes to reading mathematics, it's these days it's easiest to read things in English, because most things are translated to English or originally in English. And then there's things like, historically, there's like Arabic or Greek or German or Latin. Latin, of course, is great, and there are things being written in Latin well into the 1800s, and then there's German, which is a lot of stuff is written in German. And my problem with that is that my word shots or my dictionary, my vocabulary is pretty kaput. And it's kind of like German is its own kind of corner of vocabulary in a sense, whereas English adopts so much from the Latin. It's kind of an amalgam, that English, at least, so for French is kind of the second language to read for mathematics, because most of the words it's a Romance language, so most of the words are from Latin also, and then it's pretty legible. So it's talking about Poincare and Riemann matrices. Theory of Riemann. Their existent integrals skew symmetric, so that negative d alpha d beta equals d beta d alpha. It's skew symmetric, so it's anti-symmetric in that sense, or anti-commutative. That what's so taken from left to right is the opposite taken from right to left, or something like that. Is that I product m product prime equals this matrix 0 a star 0, and the a star equals a bar, is a positive definite Hermitian matrix. So that's for your Riemannian metric about the simplest thing that it gives there. Theorem of Jacobi. This is great. It's theorem of Abel. So here's the theorem of Abel. Let du be any one form of the first kind. Let this set P sub k be any element of a G sub n to R, and let A be a fixed point of F. Then with integration along paths on F, the sum of the integrals from A, this fixed point, to P sub h of du equals V, is a constant independent of the element pH of GNT. So after establishing these one forms and phi, this reduced that are one forms that are reducible, about the Betti numbers, B-E-T-T-I, Betti. That's the Abel theorem. And then still another classic, a sort of inverse of Abel's theorem, is this. Theorem of Jacobi. Let du therefore be a base for the one forms of the first kind. Therefore, general values of the constants v sub h extensions noted the system sum of k from 1 to p in the p unknowns of the integral from a